without further ado, take it away.
Okay, so again, thanks for coming, and thanks to Lang.Next organizing committee for inviting me. So I'm a computer architect. I design microprocessors. And so the question that you might have is, why the hell am I standing up here telling you about, languages and compilers? Well, that's a good question, and you can tell me, how much I know. But let me give you the reason why. So I have done a lot of work in parallel computer architectures. I did the early work in multi-core processors, and it was clear to me going forward that for programmers to take advantage of these sorts of architectures and the even more strange architectures coming down the pike, we need new languages and new compiler technologies. And so the title of the talk is High Performance Domain-Specific Languages, and you'll see that it has a lot to do with the published title of the talk, which is Pervasive Parallelism in Scala. Okay, so let me start with a little motivation. And so if you look at the landscape of high-performance computing today, or even what you see on your desktop, you will see heterogeneous parallel architectures, right? So you've got multi-core architectures, GPUs, potentially if you have a strange environment, maybe you might have some sort of FPGA technology, and then you might have clusters of all of these, right? And so it's the only way to get high performance, going today and going forward is of course parallelism and heterogeneous parallelism. And so what does that mean to the programmer? Well, it means that, of course, if you want to program a multi-core, you need some sort of thread programming environment, pthreads or OpenMP. If you want to program a GPU, you need some sort of data parallel programming environment, CUDA or OpenCL. If you want to program an FPGA, you need to generate some sort of hardware description language. And then if you want to cross address boundaries in a cluster, then you need some sort of message passing or pguess programming language. And so the problem is, of course, that a programmer faced with trying to develop an application, maybe they want to simulate the future, maybe they want to interact with the present either virtually or physically using some sort of robotic device, or maybe they've got a huge amount of data they want to analyze, and now in order to get the performance they need, they have to come down to these low-level architecture-specific programming models in order to do that. And so what we have here is what we're calling the programmability chasm, right? So this wide gulf between what the application developers wants to do and what the tools they have in which to do it to get high performance. And so the hypothesis that kind of drives the research that we're doing at Stanford in the Pervasive Parallelism Lab is it possible, or can you come up with a single programming language or programming representation that will run on all these machines efficiently, right, with high performance? Because if you can't do it with high performance, then you might as well not bother, because you haven't really fulfilled your aim, right? So this brings up the notion of some ideal parallel programming language that will be magically compiled into efficient representations that run on all these architectures. And so the question is sort of what might that language look like? Well, it would enable you to get very high performance. It would be general. You could run, you could try and on a variety of different application areas. And of course, it would give you very high productivity for the programmer. And the general accepted wisdom is this is a pipe dream, right? You can't do this, right? So what you do typically happens is that you get languages and environments that trade off one of the corners, right? So you can have conventional imperative programming languages that give you very high performance and are general, and you might have higher level, more interpreted sorts of languages that give you higher productivity. And what we'd like to do is to see whether domain-specific languages, which give up generality to focus on productivity and high performance, can allow you to much more easily develop applications that can achieve high performance on a variety of different architectures. And so what, I don't have to explain to this audience what a domain-specific language is. You're all familiar with them. And so the good question then is sort of how would a domain-specific language help you cross the productivity, the programmability gap? So first of all, of course, the domain-specific languages are going to raise your level of abstraction, right? So instead of dealing with the low-level programming models, you can focus on your algorithms and say more about what you want to compute rather than how it should be computed. And then the question is suppose you've got this high-level representation of your algorithm, how are you going to get high performance? So the key to getting high performance is mapping the abstractions that you have in your domain-specific language to operations or parallel patterns that can be efficiently executed on a variety of different architectures. And so what you're going to do then is use information and knowledge from the domain to help you do that translation. And within the domain-specific language, you're going to restrict what the programmer can write so that translation is going to be easy and efficient. And then lastly, you're going to be able to port to a variety of different architectures without changing the domain-specific language program, but instead just changing the compilation and runtime facilities that translate that program into something that runs efficiently on a variety of different architectures. So here's the overall picture of what we're doing in the Pervasive Parallelism Lab. The idea is you have a variety of different applications, and these applications are composed potentially of multiple domain-specific languages. So you might have one for statistics, you might have one that does physics, you might have a data analytics query language, DSL, a DSL for graph algorithms, and one may be focused on machine learning, and they might be composed in different ways. And each of them would have their own domain-specific language compiler, which would translate programs written in those languages or a combination of those each one of those languages into a variety of different heterogeneous architectures. Okay, so this, of course, means that each domain-specific language that you come up with then needs its own compiler. And so the question, or the obvious question that comes up then is, is there a way to factor out the commonality among the domain-specific languages and create some infrastructure that can be reused so that it becomes easier to create new high-performance domain-specific languages? And so a big part of our research then is developing this infrastructure that we call Delight, and it's based on Scala. It uses domain-specific languages embedded in Scala, but embedded in such a way that we can generate new programs, right? So we use staging to generate new representations of the program and the ones that can be optimized for a variety of different architectures. And so what I'm going to do in the rest of the talk is say a little bit about some of the domain-specific languages that we've been developing, one called Optimal for machine learning and another called Greenmal for graph algorithms, and then spend most of the time talking about how this infrastructure works and how we generate code for the variety of architectures. So if any time you have questions, please ask them. Okay, so let's start with the DSL called Optimal for machine learning. So everybody's aware of machine learning. The idea is to come up with patterns by analyzing data using a number of different algorithms like regression, classification, clustering, and inference. And so this is a pretty good domain for looking at parallelism because, of course, you've got large data sets and you've got long running times, especially if you're trying to do learning sorts of machine learning applications. And so also the variety of parallelism that you get is pretty varied. And it's an area in which there's lots of interest, right? And so if I talk to the researchers at Stanford doing machine learning, they have a lot of need to do high performance computation. They have a need for a high performance computation because, of course, they need to look at large data sets, right? So machine learning gets used in lots of different areas. And so we developed a domain-specific language called optimal, and the whole idea is to identify the high-level abstractions that are common in machine learning and represent these abstractions in the language as using data types and functional operators, and then use knowledge about machine learning and how these operators work to create a portable and high-performance implementation, right? So the idea is you start with a single source and you generate multiple heterogeneous targets, and this sort of thing is not possible with MATLAB today. And the key thing that's not possible with MATLAB is you can't specialize the code for the different targets in a manner that will get you very high performance. And I'll show you some results in a moment that indicate that we can do a lot better than MATLAB. So the idea is abstraction level similar or higher than MATLAB with performance equal to hard hand-coded optimized C. Okay, so the idea then is to provide a MATLAB-like description, right? So you've got data structures that you'd expect to see, vector matrix graphs and strings, and you have ways of doing vector construction, and this example shown here. And then you also have some subtypes which are specialized to particular application areas, such as image processing or the sorts of things that you do in machine learning, which is kind of learn on some training set. Then you've got implicitly parallel control structures, such as sum, gradient, and until converge for iterative algorithms. And then each of these control structures take an anonymous function. And the thing that we enforce in the anonymous function is that we restrict what you can do inside the anonymous function so that you make sure that you can get parallelism out of the resulting parallel control structure, and you don't screw up by creating dependencies that can't be parallelized. Okay, so an example here is k-means clustering, right? So first of all, you calculate the distances from the current centroids, and then you move each cluster centroid, and so this is optimal code. I don't have time to go into the details, but the overall view is it's fairly compact to represent this k-means clustering algorithm, and of course it's an iterative algorithm, and so we're using the until converged control structure, which potentially could be parallelized if you do some speculative calculation. Okay, so the whole idea then with optimal then is it restricts the set of Scala that you can use, and so it doesn't, of course, use the whole language. And the idea is to use user-defined structures and anonymous functions to get parallelism. And since you're using anonymous functions, you make sure that they're pure, and of course, functional parallelism enables easier parallel analysis. And if you want to do something in which you are mutating data, then you have to explicitly tell the compiler what data is being mutated, right? And so this, of course, allows us to do easier analysis of the program to get high performance. Okay, so because you can analyze things, you don't have to be conservative about how you find parallelism. So how about results? So here are some machine learning kernels, and the point here is just to show you that the performance of optimal is better than parallelized MATLAB, and it can run on a variety of different architectures. So what I'm showing here are 6 kernels running on multi-core and GPU architectures, and the optimal performance is in red, and we were looking at execution time, so lower is better. And so what you see is, across the different kernels, that the red bars are typically lower, and sometimes in the case of the GPU, a lot lower. Okay, so the point here is that you can get very easy highly productive programs, or easy to develop highly productive programs with performance which is much better than MATLAB. And if I had time, I'd show you some more performance numbers that show that it is actually pretty close to highly optimized C. Okay, so that's the first DSL, just to give you a flavor of the domain-specific languages that we're looking at. A second domain-specific language we're looking at is one we're calling Greenmal, and this one is focused on graph analysis. And so the idea here is, of course, that you've got some graph that you'd like to analyze. So, for example, some movie database, and you want to understand sort of, who's the most important Australian actor, or how many actors have appeared in movies together, and so do these actors often appear in movies together? And so the idea is to come up with a domain-specific language which makes this much easier to do, right? So the idea is that graphs are large and require a fair amount of processing, and they have the potential to do, this processing has the potential to be done in parallel. And the problem is you need to develop both a algorithm that implements your graph analysis, and of course you want it to be parallel at the same time. And so the way that the Greenmal is structured is that you have a graph algorithm which you describe using the primitives in the language, and these primitives, of course, give you the core parts of a graph analysis algorithm, and they're defined so that you have inherent parallelism. And then the idea then is to take these abstractions that are described in the graph algorithm and implement them using templates that work on a variety of different architectures. So the idea is these templates can be reused in ways that you couldn't reuse them if you just had a library of functions. And so in between, you want to optimize the graph algorithm representation using knowledge about the particular graph analysis that you're doing. So in this case, we're looking at social network type graphs which have a real world structure, right? And so we want to take advantage of that to analyze our and optimize our graph algorithm. So as an example, here's a well-known graph algorithm called betweenness centrality, and here you want to find out who's the most popular person in some sort of a social network. So is it Kevin Bacon, or is it this guy who appeared in Slumdog Millionaire? Probably not. He's probably on the edge, right? And so the idea is that you want to find that the graph algorithm is essentially find the number of shortest paths that go through a particular node. And the original presentation of this graph algorithm is shown here. But if you look at this in detail, what you'll find is that is essentially is a breadth-first search in which you compute some value called sigma, and then a reverse breadth-first search in which you combine that with a delta to come up with betweenness centrality. And if you describe this algorithm in Greenmal, you can describe it using the in breadth first search primitive and the in reverse breadth first search primitive in a much more natural way than the original description of the algorithm. Because the original description of the algorithm had breadth first search encoded in the algorithm, and if you abstract that out, you can come up with a much simpler description. Yeah.
So how many of these kinds of in BFS and in out BFS have, and is there a facility for the user at Greenmal to make up their own new construct?
We don't have a large number. So breadth first search, iteration over the graph elements, all the neighbors of a particular vertex, depth first search, which of course is inherently sequential, and so we don't have, it's not easy for the user to develop their own. And if the user wanted to extend the primitives in green mile, then they would have to change the compiler, right? So that's the issue, right? So, of course, we don't cover all algorithms, and in fact, green mile, as I said, is focused on social networks, right? So for other sorts of networks, so part of a domain-specific language is the assumptions that you make about the data, right? And so if you don't if you come with a graph that has different assumptions, then maybe you want to apply different algorithms, right? So maybe that's a different DSL, yeah.
So in large-scale graph algorithms, it's essentially to control. Thank you. So in large-scale graph-based algorithms, it's necessary to control very exactly the representation, the layout of the data in memory, and also the distribution of data across computers. How do you address these two issues?
So the layout of the data in memory, of course, is just because you want to minimize the footprint of the data, right? So that can be optimized because you know what the graph looks like, right? You know what the graph algorithm looks like, and you've specified what metadata you have on in the graph. Now, as far as distribution, what we have is we have a way of generating the programs that will run in the Prego environment. So I can tell you more about that offline, but distribution is a very hard problem. The original version of GreenMile was focused on shared memory implementations on multi-core and GPU. But if you want to go to distribution, we can do that too, but not just, we need to add some more constraints about how we generate the code, but it's possible. So we have parallel assignment, we've got these breadth first search primitives, parallel iteration, and then of course reduction operators. And so, the power of GreenMile is, of course, that it eliminates the programmer from having to explicitly write a parallel program, and it's better than using a library because it's more flexible and can be optimized for the particular algorithm that you have. So this just shows, the lines of GreenMile versus, what happens if you try and code these same algorithms up explicitly using C++ and OpenMP, and the performance is very similar. Okay, so then the question is sort of how do you come up with optimized code? Well, you need to do some architecture-independent optimizations based on the algorithm described in GreenMile, and some architecture-dependent optimizations which depend on what particular target you're focusing on. And I don't have time to go into details, but the performance of, I'm an architect, so I'm going to show you some performance numbers, right? So this is a couple of, between the centrality and what we're showing here is compared to well-publicized library, we do a lot better, depending, and it doesn't matter whether the graph is RMAT or it's uniform, we still do better. Okay, so that's just kind of an introduction to DSLs, and now the question is, okay, what about DSL? What if you're not doing graphs and you're not doing machine learning? Maybe you want to focus on some other sorts of areas, right? So here are a bunch of different areas that we're looking at developing DSLs for, and maybe you've got your own favorite domain in which you'd like to develop a DSL. So now the question is sort of, how do you make it easier to develop new DSLs? Because there's a lot of work that you have to do, right? You've got to sit with the domain experts, or maybe you're the domain expert, and figure out what the right abstractions are. You've got to develop a compiler for those abstractions and figure out how to optimize the parallelism and generate parallelism for a variety of different architectures. And then you've got to deal with all the low-level issues which are required to get high performance, right? If you don't do this right, your performance will not be good, and no one will use your high-performance DSL because it's not high performance, right? And so what we'd like to do is to see whether you can come up with an infrastructure which makes this whole development of these high-performance DSLs easier, okay? So here's the approach that we're calling Delight. The idea is to embed the DSLs in Scala and leverage Scala's type checking and parsing capabilities, and then create a reusable intermediate representation that can be optimized at multiple levels. It can be optimized at the domain-specific level, it can be optimized at the parallelism level, it can be optimized at the Scala level, and then the idea is that within this IR, we're going to use patterns that can be, you can think of this as a parallel instruction set, and these patterns then can be optimized for different architectures, okay? And so these patterns we're calling delight ops, okay? So let's talk about how we do this, but before we do that, let me just say a few words about why we decided to use Scala, okay? So Scala has a very flexible and overloadable syntax, which makes it easy to develop DSLs that look natural and can be represented in, you can represent methods in an infix notation, and so you can make things look pretty natural. And of course, it's functional, which means that a lot of your DSLs, of course, you want to be functional so that you can make it easier to extract parallelism, because of course, if functions are pure, then they have no side effects. It's got a very expressive type system, which means, of course, that we can use this type system to enable the transformation of the DSL programs into an intermediate representation, and we can do this in a way that hides some of the machinery that we're using, and it does it in a safe way. And it also has this ability to do modular development, which means that we can mix and match what parts of DSL capabilities we want in each DSL. So we can have a variety of different capabilities, and we can kind of put them in different DSLs in a very flexible way. So here's the way things work in Delight. We have a number of DSLs, so we might have optimal or the Delight version of Greenmile that we call Optograph. And our goal, of course, is to generate code for a heterogeneous architecture. So first of all, we're going to embed our DSLs in Scala. Then we're going to use modular staging to generate a new version of the program. And the new version of the program is going to be developed by using an intermediate representation that expresses these parallel patterns and can and allows optimizations, both static optimizations and optimizations for specific heterogeneous parallel targets. And then once we have a representation that expresses the parallelism in the application, then we can use runtime information from the data to further optimize and generate code that runs efficiently on a variety of targets. So let me briefly go through, in the time that remains, how we do this. So we start out with in this example, let's think about converting the DSL program into an intermediate representation, right? So you start out at the user level with some set of domain abstractions. In this example, we're going to use vector and matrix. And then it's the DSL author, of course, defines these domain operations. And then the next thing the DSL author has to do is to figure out how to convert these domain abstractions into into the delight ops, right? And so the other thing that the DSL author has to do is to figure out what sort of domain knowledge they're going to use to analyze and optimize things at the domain operation level. Okay, so how do you build an IR? So the essential way to do that is to instead of actually executing the method, you want to build an intermediate representation. And so this is just an example for this simple expression here. And you're going to use the ability to do infix methods, and you're going to create representation. So the way that we do this is that we use abstract type constructors within Scala. And so the abstract type construction means that the type can have a range of different implementations of matrix. And so the way that this works is you have both a definition and an implementation. And so the details are in the matrix arith trait. And the way that this works then is that operations on these abstract type constructors are lifted into the intermediate representation. And so we need to be able to lift more than just data types. We need to lift the other parts of Scala so that we can analyze the whole program. And so these are the set of things that we currently lift, and these are what we don't currently lift, right? So methods are all executed in line, and we don't do much with classes. Okay, so now that we have an intermediate representation, we can optimize it using rewrite rules and pattern matching, which of course Scala also provides. And so now we have a set of delight ops which can be optimized at the parallelism and locality level, right? And so these ops can be optimized by the delight environment. So we have a bunch of patterns, map, filter, reduce, hash, breadth first search, and the like, which we know how to execute efficiently on a variety of different architectures, right? So the goal of the DSL author then is to map domain abstractions after they may have been manipulated and optimized into these domain operations, and then delight handles the parallel optimization and code generation for these ops, and then now, of course, you get to leverage this across multiple DSLs. Okay, so one of the optimizations which we use extensively is fusing, right? So we fuse ops that can be fused together, and this gives us a lot of performance benefit. And the last thing, of course, we do is because we are extending the generic delight op, we can get scalar optimizations too. Okay, so we also analyze data structures, so we allow the DSL user to define their own data structures, and then of course we can analyze them. Okay, so one of the things you might want to do is reason about what part of the data structure is getting used. So if you have a real and imaginary part, and only the real part is changing, then of course why generate the data. So the way that we do this, of course, is we convert everything from an array of structures to a structure of arrays. You figure out what part is important, and then you can fuse the things. You create individual loops for each part of the structure, for each array composing the structure, and then you get rid of loops you don't need, and then you can fuse them all back together again. Okay? So then once you have an optimized intermediate representation, now you can generate code for a variety of targets. And so you have a Scala target, a CUDA target, and a OpenMP target. And currently only the Scala target has to succeed. And so you can always, of course, run your code on a multi-core device. And if you've got some other sort of architecture, then you may or may not be able to execute your kernel, depending on whether you've got a generator, right? So here's the overall picture. You use the Scala embedding framework and the abstract types to embed your DSL application. When you execute that program, instead of executing the program in normal fashion, you stage it and create an intermediate representation, which can be analyzed at multiple different levels. And then once you've analyzed it and optimized it, you generate code. And what you generate is what we call a delight execution graph, which has kernels. And each of these kernels has multiple instantiations, so that can run on different architectures. And then we also, of course, know about what data structures you're using. So here's the overview. So front-end language defined as abstract classes. Operations are defined as IR nodes. data structures are these things that have concrete implementation in the back end. You've got code generators for the delight ops, and you may or may not have domain-specific optimization. So here are a bunch of DSLs that we've implemented so far. Talked about optimal. Optical is a link-like embedding inside of Scala. We have OptiGraph, which is green mile on delight. We've got OptiMesh, which is kind of a physics-based partial differential equation solver on meshes. We have OptiCollections, which is essentially just Scala collections, but using delight ops, implemented using delight ops. So regular Scala collections, but using delight ops. And what we've shown is we can get very good performance on all of these, and much better performance than regular Scala collections. You know, in our we looked at comparison to Link, and we were able to do better performance than Link. But you know, we could see, you know, maybe we weren't running Link in its most optimized way, but we were running it in parallel, and we were able to do get very good performance. And in terms of OptiGraph, our performance is comparable to what you can get with the C++ implementation of green mile. So the question then is, how big a set of delight ops do you need, right? And you know, what optimization requirements do you have? Do you need as you add DSLs, right? Because you know, the point of an infrastructure is that it should support a wide variety of different DSLs. And so this just shows the DSLs that we have implemented so far and the delight ops we've used. And what we see is a fair amount of reuse among the delight ops. And then we also show the optimizations that are performed and how each of the DSLs that we've implemented so far use those optimizations. And so we're pretty happy with the set of delight ops. And of course, as we add more DSLs, we potentially will add more delight ops, but we are getting to some sort of plateau in the increase in the number of delight ops. Of course, I didn't do most of this work. You know, the collaborators, especially the graduate students, of course, did most of the work. But the collaborators, Pat Hanrahan, especially on the DSL called List, and Martin Odersky has, of course, been working with us to make the Scala compiler able to perform this lifting process. So we have a special version of the Scala compiler called Scala Virtualize, which enables you to lift most of Scala, all the pieces that I showed. And as I said, the students are the ones who have done most of the work. So in conclusions then, DSLs have the potential to provide this great benefit of both productivity and potentially higher performance because they allow the compiler to know more about what the program is doing and to optimize in a domain-specific fashion. And so in order to enable more DSLs to take advantage of these sorts of capabilities and make it easier to develop DSLs in general, we need powerful underlying base languages which we can embed these DSLs into that provide the sort of facilities that are going to be required to enable us to more easily come up with optimized DSL implementations. And so our early work on Delight and Scala shows that this is indeed possible and you can get pretty good results. And unfortunately, of course, I didn't have time here to go into all the details, but I've given you a sense of what we've done and what's possible, and I can probably have time for a couple questions for you. Yeah?
So I'm wondering, do the DSLs compose? So like if...
Very good question, and I didn't have time to go through that. But yes, you want the DSLs to compose, and so the way that we've done that is to have scopes, right? And then you have global data structures that can move between the DSLs. And then you also want to be able to layer DSLs on top of one another, right? So for instance, we did optimal and we figured out that the core of optimal is matrix and linear algebra, and we can use that in another DSL based on convex optimization, right? So you want a core DSL, you want to be able to layer, and Scala makes that fairly easy to do. Another question.
Any questions?
Okay.
Okay. Well,
Thanks.
Thanks a lot.